Ladies and gentlemen, including future ladies and gentlemen who are listening to this webinar. Welcome to my last webinar for the year before I take a Christmas break and rejoin you all in January of next year. So this is the last one, which is obviously very sad, but obviously next year is going to be even bigger and better. I'm not sure what that means. So today we're going to be talking about why redundant systems aren't always redundant. And this title is a little bit of a misnomer, so to speak, because the problem with redundancy, or what most people think redundant means, is that redundant, I can see I've misspelt redundant, is redundant often means a very specific thing to each and every one of us. It usually implies that we have a component which is able to do something that another component, for whatever reason, can't do. But there's so many different ways to incorporate redundancy into your system. But before we even talk about redundancy, let's talk about why redundancy is a thing. And redundancy, the first time we start even thinking about redundancy or things like redundancy are when we have got to that point in our design where, for whatever reason, we can't do anything more to tolerate or to address your failure mechanisms. Perhaps the components in question are as reliable as it can possibly be as of right now. You could potentially make them more reliable, but at prohibitive cost, or for whatever reason, you just cannot inherently design those vital few failure mechanisms out of your system. Which means that if that's the case, the next step is to start thinking about what we call fault tolerance. Because if you can't design those failure mechanisms out, that means the faults that trigger those failure mechanisms need to be tolerated. So let's look at a pump. And in this case, a pump, which is obviously pumping fluid, is the weakest point in our design, even after Vermeer, Holt, derating, and every other DFR activity you can think of. But our reliability allocation shows it needs to be even more reliable than it currently is for our system to meet requirements. And so we somehow need to do something that doesn't necessarily change how our pump works. So when we think about pumps, one of the things that pumps are sort of relatively famous for, so to speak, is that they have a butter zone. They have a region where they would optimally work, and that means they are most happy, for lack of a better term, in that region. And you can see here on this chart, we have on the top right hand corner, we have the flow rate and efficiency on the vertical axis, and the efficiency is obviously peaks at a relatively small region where the flow rate essentially supports optimum efficiency. And that's because impellers within pumps are designed around a nominal flow rate. When you deviate away from that flow rate, it's almost like an aircraft stalling. Those impellers don't work nearly as well. The other thing about that high efficiency zone is that is almost certainly a region of high reliability, because if you need to pump fluid at a non-optimal place, then you're essentially using a lot of energy to achieve not a lot of outcome. So you typically provide more energy to your pump to try and meet the requirements, and all of a sudden your pump is churning through its life. So one approach to tolerating faults is to replace this pump with another pump, which, although is perhaps specified in a very similar way, has a larger region of higher reliability, because for whatever reason it's designed in a way to tolerate or to promote efficiency in a wider band of flow rates. And this is what we call variability control, where we use components that can tolerate larger variation in inputs caused by failures or faults in other components. So that's one way of tolerating faults. Another way of tolerating faults is, or at least for our pump, is to try and protect it from, for example, pressure spikes. And these pressure spikes would be obviously upstream, and the regulator can make sure those pressure spikes don't go down the pipe hit our propeller and destroy whatever is left inside. And so this is called fault containment, the prevention of the propagation of a failure mechanism across a system due to a fault in a single component. So now we are starting to tolerate faults with with variability control in our pump and a regulator which contains faults upstream. But then there are things where we might have, for example, scenarios where we might have a leaking pump, which is a problem. It's not a problem in that allows the pump won't work, but it is perhaps a harbinger of doom, so to speak. So another way of tolerating faults is installing mechanisms, installing alarms, installing sensors to identify or diagnose a fault when it occurs, noting that a fault is not a failure yet. So if we can find faults when they occur before they propagate to a full-on failure, that allows us to do something about it. And diagnosing is essentially all about finding when and where. So fault detection means working out that a fault has occurred. And that's where we use things like built-in testing, built-in self-testing, built-in test equipment, which are different ways of describing a very similar capability. And when we talk about software, this is equivalent to what we call error handling. And then there is another scenario, which technically isn't fault tolerance, but I like including it here because I think it is in a way, and that is proactive maintenance, where we address faults before they become failures. And the reason why that's important is because you can diagnose as much as you want, but unless you're going to do something about it, then it doesn't mean all you do is admire the problem. So this is technically not considered fault tolerance, but this is where you start thinking about what you do in response to diagnosing faults before things happen. And proactive maintenance, addressing faults before they become failures, involves things like condition-based maintenance, where you have sensors which detect how far a crack is propagating, or if there is a leak, or if the outbound pressure is not where it needs to be, et cetera, et cetera. In a long story short, we want to identify disturbances from the optimal operating conditions that might be symptoms or early warning of a failure. And so that's another way we can tolerate faults. Yet another way is through a thing called reversion, or sometimes it's called derating, where whenever we have a problem, we put that pump into a suboptimal operational state that prevents imminent failure caused by an isolated fault. So that usually means that we ask our pump to pump at a lower flow rate. So we're still doing something, but not everything the requirements say we need to do. But it's better than having a pump which has failed that can do nothing. And this usually involves software where we have some sort of automatic trigger for this derating or reversion. And essentially we want to save our pump from complete failure. We're starting to see how faults can impact or degrade our system's performance, but we still are doing something in a very clever way and make sure it doesn't destroy our system. And the last thing we can do to tolerate faults is incorporate redundancy, the duplication of components or functions. And in this case, we have two pumps that are designed to be able to satisfy systemic requirements if only one of them is working. So how does redundancy improve reliability? Well, from a very basic concept, we can see that if we have two things and we only need one of those things to work, we have more ways for our system to work, which is the opposite to a series system, where we have more ways for a system that a system can fail. And so we can actually calculate system reliability by focusing first on failure probability. In this case, the failure probability of the system at time or usage t is represented by this expression here, F subscript system, T is in brackets. So this is the failure probability of our system, which incorporates redundancy. Now, if we have our two-pump redundant system, we know that the failure probability of the system is simply equal to the product of the failure probabilities of each pump. And because failure probabilities are between 0 and 1, when you multiply them together, you get an even smaller number. So you always see system failure probability go down when you incorporate redundancy. And you can do this in a way where you can have as many redundant systems as you want. And then each the system failure probability is simply equal to the product of all the individual component failure probabilities. In this case, this expression represents a scenario where we have n total components where all but one of them are what we call redundant. So that is the mathematics behind it. Multiply all the failure probabilities to get the system failure probability. But of course, we're interested in reliability. So the reliability of a redundant system looks like this, where the reliability of the system is equal to 1 minus the product of 1 minus the reliabilities for each one of those redundant components. We'll go through a worked example, which is in your guidebook, so you can either follow with me or do it in your own time. We're going to look at this 2-pump redundant system, and we want to know what the reliability of the system at 2 years is if the reliability of each pump at 2 years is 70%. So we have to use this equation here. We know that there are 2 parallel components, and we use the term parallel for redundancy a lot because it looks like our redundant components are quite literally embedded in a parallel way into our system. That's where the term parallel comes from. And so we have 2 parallel components. And so in this case, n is equal to 2. And the reliability of each pump at 2 years is 70%. So we can take that expression out or substitute it with 0.7, which is another way of saying 70%. Now we can start evaluating our formula. 1 minus 0.7 is equal to 0.3. So let's substitute 0.3 into our equation. Now we just got a product of these two. So let's expand this out. So 0.3 times 0.3 equals 1 minus 0.09. So the reliability of our system at 2 years is 0.91 or 91%. Remembering that the reliability of an individual pump at 2 years was 70%. So you can see we have improved reliability markedly. So let's look at the reliability curve of our pump because reliability changes over time. And you can see for this particular pump, as is the case for most pumps, we have an initial region of wear in on our reliability curve. I do plenty of webinars where we talk about how you can identify these characteristics from the shapes of curves. We have this little initial dip which peters out. So we have some wear in. So there's infant mortality or perhaps failures caused by installation and manufacturing defects. Then we have this more reverse S shape, steeper drop where our system starts wearing out. And we can use that equation that we just went through to calculate the reliability of our system at any point in time. And we get this blue reliability curve here. So you can see that whenever we have redundancy, we increase reliability. In fact, redundancy is one of the most effective ways of dealing with infant mortality or wear in. You can see the blue line is almost 100% in that region where we had that little initial dip of infant mortality or wear in. And over time, when our pump reliability approaches 0, the extent to which parallel systems improve, redundant components improve reliability decreases. But as a rule, when we're interested in, for example, the first 10% of our systems failing, which is not an uncommon figure, you can see that by having our redundant pump system, the time by which we expect 10% of our systems to have failed is almost doubled. You can just see where the red line crosses 90%, compare that to where the blue line crosses 90%. But these redundancy equations only work if failure is independent. And this is where I want to start thinking about what redundancy means. Redundancy there is no such thing as a typical case or model for redundancy. Virtually every scenario has its own unique calculations for how those redundant components are going to impact system reliability. Even though I just seemingly gave you some equations which apparently give you the answer. But that only works if failure is independent. And we'll look at what independent failure means. So let's go back to our two redundant pump system, which is something you see quite a lot. Now, one way we can observe failure that is not independent is when we have this thing called common cause failure. And what common cause failure means essentially is the failure events of one pump influences the failure event of the other. I can see William Harwood made a comment. We're going to come back to your very sage comment, William, because it's something I'm going to address very shortly. So let's just say for in one scenario that when a pump fails and it's beneath the other pump, it catches fire, which is unusual for a pump, but it can happen. But if that pump beneath the redundant pump catches fire, well, of course, now the top pump is supposed to take over the load, but it's essentially sitting on top of a bonfire. Now, it too will eventually catch fire, you might think, which means that when we had that first pump failed, it failed in a way where it essentially triggered the imminent failure of the other pump. So we didn't really have redundancy in the way those equations would suggest. Now, this is one of the easiest ways to look at common cause failure. But where one pump fails or one component fails in a very critical or catastrophic way, and you can see how it would then trigger the failure of another pump. Does anyone have any idea how else we might have common cause failure besides a scenario where one component fails and essentially damages another pump or another component as a result of that failure event? Is there any scenario anyone can think of where we might still have common cause failure, but not have one component failing, damaging? Well, the housing breaks and we lose water. Well, that's how a single pump might fail, but we need to link it to the failure for the next one. Thanks for that feedback on the workbook, Brian. William suggested contamination in flow. So what does that mean, William? If you could expand upon that. Contamination in the flow. How might that result in failure that is electrical circuit is overloaded by the failed pump? Okay, loss of power, common supply. There we go, John, that's a good one. Failure of the T-joint. Yeah, now we're starting to talk. Pipe blockage upstream. Well, that might be a failure of the pipe itself. I might not necessarily, you might say the T-joint is something similar as well. But I think we're starting to think about what I'm asking you to think about, which is factors that are outside a single pump. There we go. Both pumps are seeing bad contamination in what is pumped. Fantastic. And so that's where we see scenarios of freezing temperatures that would ruin the day of any pump. You could argue that if freezing temperatures are going to freeze one pump and then fail, then that freezing temperature is also going to freeze the other pump and have it fail. So now we're starting to think about things outside of our single pumps. So, for example, the restriction in the upstream pipe can limit intake or head pressure, causing cavitation, which leads to failure of both pumps, which is similar to contamination, upstream contamination. It's also similar to freezing temperatures, where all of a sudden it doesn't matter if you've got redundancy. If neither pump's designed to work below 0 degrees Celsius, you don't have redundancy anymore. If the shafts were installed by the same incompetent team, and there is a higher chance they both misalign. Now, incompetence is a very malicious word, but just understand that in many ways, when we install a brand new pump into an asset, many teams are incompetent because that's the first time they've ever used or ever installed that pump. And I mean incompetent in a very clinical way. They might still be very fastidious workers, but if they weren't trained how to install this brand new pump properly, technically they're incompetent in a way. Then we have the same power supply failing. And if the maintenance regime, this is a big one, if the maintenance regime is not appropriate, they will also both fail. We're going to talk about this a little bit later on. Maintenance regime, selected seals that were incompatible with the fluid. Fantastic, Brian. So we have a factor which obviously one pump won't, and with failure of one pump won't induce the failure of another one. But because both pumps have the same defect present, we really limit the extent to which we have redundancy. So another way of looking at redundancy is a very different place, especially with common cause failure, is a very, let's just say, active consideration. So let's look at these two pumps where the high reliability zone of each pump is 25 to 50 gallons per minute. And the system requires 75 gallons per minute to be pumped. So this means that if each pump is happily pumping 37.5 gallons per minute, which is right in the middle of its high reliability zone, our system works. But let's just say now that one of our pumps fail. Now, our system's still working because our pumps can pump up to 75 gallons per minute. But this is now a challenge. This is now well and truly outside its high reliability zone. So even though our system hasn't failed, we are in a less than optimal scenario where one pump is doing more work than it's designed to do. It's still working, but because it's working harder or outside its optimal zone, its failure is now going to occur a lot faster. This is actually another form of dependence. It's called load sharing, because the failure of our second remaining pump is inextricably linked to the failure of the first pump. And so we have another form of dependence in load sharing scenarios. William, mentioned that failure from common cause thermal coal failure causes space shuttle O-ring failure in redundant O-rings, which is true. You could even go one step further that the common cause amongst that was a complete lack of engineering, let's just say, competence in the decision-making of NASA at the time. And we're going to touch on some of these cultural things later on. So load sharing, which is where we have two components which work together to provide an output. In many cases, those two components, one component is all that's needed, but ideally you want the load to be shared. Well, it's another form of dependent failure. In a way, it does have a common cause, but we don't typically call this common cause failure. And this is another scenario where failure is not independent. Then there is another type of a setup where you design this into your system where you have a switching system. And this switching system, we have the main pump at the very top, and it's happily pumping away, meets the system requirements, and something bad happens in the top pump, and then our valve or our switch turns and starts the other pump working to take over from the first pump. This is, like I said, a switching system, which is another form of dependence, because you don't know how long the second pump's going to work unless you know how or when that first pump failed. And so these are the sorts of things that we see in the real world around us, where we have not only common cause failure, but we have these things designed into our system where they actually reduce this or eliminate this assumption of independence. Now, then there's things like standby and active standby and cold standby. And those standby scenarios are analogous to, in a way, the switching system, where the idea behind a switching system is you want to keep that redundant component as pristine as possible so that it's not incurring damage while the main component is working away. That's something that doesn't happen when we're looking at genuinely independent redundant components, because the independent redundant components are accumulating damage regardless of whether or not the other one is still working. And that's not always the case. And so switching systems are a deliberate attempt to try and minimize the damage that's being incurred on the redundant component. And that only works when we are able to transfer essentially the load or the demand or whatever you want to call it from the main component to the redundant component in a very controlled and active way with that switch. And then we have to concern ourselves with, well, what does pristine mean? Because in many cases, having a pump just sitting there not doing anything is one of the worst things you can do for a pump. The seals will deteriorate, all sorts of other things can happen. So you don't just necessarily want that pump to be sitting there idle. We call that cold standby. Now, in some cases, having that redundant component in a cold standby state is what needs to happen. But sometimes we need to have it warm standby, where it's being asked to do some, but not all of the demand. And the reason why I want it to do some is that little bit of effort we require it to do allows fluid to continue to move through that pump, and otherwise make sure seals don't perish and other bad things not occur either. Then we have hot redundancy, where essentially it's being asked to do the same thing as a main component, which in many cases hot redundancy becomes analogous to simple independent redundant components. Then, as William points out, that we need to now, Michael points out, we now need to deal with the failure probability of the switch. And the equation that you need to use for a switching system, which incorporates the failure probability of the switch, is also considerably complex. And the other thing that William points out is when pump one fails in a standby system, you no longer have redundancy, which is true. I mean, as soon as one of those pumps fail, you don't have redundancy, but to an extent, that's the sort of scenario you're actually designing into your system. So there is no such thing as redundancy, so to speak. And you can't see my air quotation marks at this end of this webinar, but there is no single definitive typical textbook redundant configuration. Virtually every scenario has a unique flavor of redundancy where you can't just simply use the same equation over and over again. Each one of these requires specific equations based on how these dependent failures occur. So let's look at an example. Let's look at time to failure, or create a chart where time to failure is on the horizontal axis. And we're going to create a density curve for failure. That is, we're going to create this curve here, which represents the reliability of a single pump. Or actually represents the failure density of a single pump. And you can see that essentially this means at the peak of this bell curve, that represents the region where we're going to expect most pumps to fail. You can see some pumps are starting to fail after 2 months. You can see that most pumps have failed by 8 months, but right in the middle, we have this region where we have a peak expectation of failure. And this is a bell curve, which means that our pump is wearing out. So if you learn nothing else from this webinar today, if you ever see a failure density curve or a probability density function, which has a bell curve, which represents the random active failure, then if it has a bell shape, it has a peak, even if it looks a little bit like a hill or a mountain, then you know that your system is wearing out. So let's just say this is the bell curve, which represents the time to failure for our pump. Then if we can use this bell curve to, for example, work out when we expect 99% of our pumps to still be working. Or another way of saying that is, no random hand of failure today, Fred. It has cramps. So in this case, we have this curve telling us when we expect 1% of our things to fail. There's simply 1% of our area is under the curve. So if we have no redundancy, then 1% of our systems will have failed by that time represented by that arrow. Now, if we introduce 2 pumps, then the revised bell curve of our two redundant pump system looks like this. You can see it's being pushed to the right. And that means that if we find the area, 1% of the area under our new bell curve, with one redundant pump, so a total of 2 pumps, see the time by which we expect 1% of our systems to have failed is extended considerably. It goes up by about 39%. And if we add another redundant pump, so now we have 3 pumps, 2 of them redundant, then the time by which we expect 1% of our system to have failed increases by another 13%. And so you can see that we can, if every time we introduce another redundant pump, reliability or the B1 life or whatever reliability metric it is you're focusing on, it will get better. But the extent to which it gets better decreases for every additional redundant component you add. Now, when it comes to common cause failures, if you have no idea about the extent to which common cause failures is ruining your day, we have found through observation that 1 in 10 failures are caused by have a common cause, I should say. Now, what this does means that if we do the modeling, or we model the 1 in 10 of our failures having a common cause, which essentially means that when a failure event comes along, 10% of the time, redundancy is automatically taken out of the calculation. So this will reduce reliability and create these ever so slightly different green bell curves of a system which has 1 and 2 redundant pumps, but now 1 in 10 failures have a common cause. Now you might say, well, those green curves are pretty close to those red curves, and that's okay. Well, yeah, you're right, except if you're making multi-million-dollar decisions based on how long it takes for those first 1% of your pumps to fail. So what does this mean? Well, it means that instead of increasing your B1 life, or the time by which you expect your 1% of your systems to have failed, instead of it being increased 39% when you add a redundant pump, it only increases 30%. And it also means that if you want to add another redundant pump, instead of having that B1 life extended by 13%, it's now only extended by 6%. Now, this could be a big deal if you're basing very important servicing intervals or warranty periods on your reliability analysis. And so this is very important to understand when it comes to redundancy. Same thing with switching systems, same thing with everything else we've talked about today. So when it comes to redundancy, there is a decreasing benefit for each additional component. Common cause failure diminishes the positive benefit of redundancy. And there is an increasing benefit when we're interested in a smaller number of initial failures. That is, when we're interested in our B1 life, our B5 life, our B10 life, the time by which it takes for our first 10% of our things to have failed, for example. Now, Williams raises a really good point. We don't just want to have redundancy willy-nilly, because if we have redundant components, now we need to maintain them as well. So it's not just that, but there are more cultural problems as well. Because when we have redundancy, some genius managers can essentially breathe a sigh of relief, because this introduces a sense of security. It also means that fault-tolerant components can hide the fact that a fault exists. So sometimes we might not know that a redundant pump has failed because our system's still working happily. And that means we aren't aware that we can be conducting maintenance on that failed pump to restore redundancy, because as of right now, we don't have redundancy, especially if one of those components fails without us knowing about it. And as William pointed out, we have all these additional things to maintain. But beyond that, it means we add weight and cost. And that's a big deal for not only electronic componentry, but things like aircraft, where redundancy was often mandated for certain scenarios. And as our engines and avionics became more and more reliable, there was a push to reduce this mandatory redundancy thing, where instead of having to have 2 engines to fly certain routes, you only needed to have 1 engine, and that can open up routes to a whole bunch of new aircraft, which is obviously a good thing, especially if the reliability analysis suggests that. But beyond that, we can get lazy. I often see, for example, in the CRE body of knowledge, that essentially they say it is okay to use inferior parts and components if you have redundancy, which is insane. That is not the point. When designers worked out they needed to have redundant components, they don't take into consideration your buffoonery and the pursuit for the cheap and nasty approach. That is something that only incompetent engineers and managers who have no idea think is okay. We can also do things like delay or defer maintenance because our system is fault tolerant, so to speak. We don't need to maintain it this month because it's got redundancy, it's got a backup. So we can skip maintenance this month. Well, again, the designers put that redundant component in there for a reason. So what that means is that we start getting this mindset where essentially we stop thinking. And a really good example of us stopping thinking is the Royal Australian Navy, which I dare say a lot of my listeners won't know too much about. But a lot of, long story short, is that HMAS Canimbla and many other vessels were frequently put to sea with broken and redundant components. And then one of the reasons why is because the captains of these vessels only had 2 years in their posting to go and sail the seven seas, so to speak. And if there were maintenance issues and engineering issues, which there were, because the whole engineering capability had essentially been degraded over time, they would find any reason to put to sea. So during their 2 years of power, they would not miss out on what was essentially the pinnacle of their career at that time. And it created a culture where you had to prove something was wrong for you not to launch. And that meant that we had this culture. I'm ex-army, so this wasn't me, but I've seen plenty of instances in my military career of just very bad decision making. That meant that the HMAS Tobruk was unable to support cyclone disaster relief. Essentially, when the Minister of Defence was being told this vessel was ready to go and support Innisfail up in far north Queensland, which was decimated from a cyclone called Cyclone Yazi, it happened to be floating aimlessly across Sydney Harbour with an onboard fire and a fair bit of ammunition. They were able to rectify the issue before a disaster occurred. But suffice to say, after all the years of this thing being communicated as being ready to go, when the question was asked, it certainly was not. So redundancy can have a negative effect on culture because in this scenario, at least, the assumption was a ship is safe to sail unless proven otherwise. Now, this is all great for hardware, but what about software? Can we have redundancy in software? And the answer is absolutely yes, but we need to be careful about that. So let's look at our two pumps, which is a very classic hardware redundancy scenario. But now let's try and change this in a very, let's just say, hybrid way to a software scenario. The idea of our system here is that we want to sort numbers. So we have a sorting algorithm. We have two sorting algorithm programs, and they're constructed in redundancy, so to speak. And what we want to do is we want to have numbers go into our system and then come out the other end of our system sorted. So that's what a sorting algorithm does. Now, the problem with this is the only way software fails is if there is a human error, because software is usually pretty good at doing exactly what it's told. In fact, software, as a rule, always does what it's told. So when we have a problem with software, we're talking about human errors. And that means that if we look at the code for one algorithm, in this case, is the bubble sort algorithm, this is what it should look like. Let's just say, sorry, before we get into that, I need to describe how the bubble sort algorithm works. And the bubble sort algorithm works, all this code here, it's quite simple. Just essentially means that for every set of numbers that are input to the system, we look at numbers, two numbers at a time. So the first thing that happens in our bubble sort algorithm is that numbers 7 and 3 are compared. Now, if the second number is lower than the first number, those numbers are switched. Then we look at the next two numbers, and the next two numbers, well, they're switched again, and there's no switch there. Now, what happens, we go back to the start, and if the very first two numbers are sorted, that is, the first number is lower than the second number, the bubble sort algorithm essentially applies a check mark. And that check mark is going to apply to those first two numbers only. When we look at the second two numbers, you can see that these two numbers are not sorted. And so we have a cross. That cross erases every single check mark. So the bubble sort algorithm then swaps those two numbers and keeps going through the rest and keeps swapping. And because we didn't have because we had a cross, then the algorithm, keeps going and going. It keeps going until there are, in this case, 5 successive ticks. So now we have 1 tick, 2 ticks, 3 ticks, 4 ticks, 5 ticks, and our algorithm is now done, and we have our numbers sorted. So that's what this code here represents. Now let's just say, in my haste to write this code, I made an error. Instead of this greater than sign, I put an equal sign, which is a coding error. And this is what's going to cause a failure. So the problem with this is that if I have this same defective code in redundancy, then I essentially replicate the defect in a very precise way. So it doesn't matter if I have redundant programs, if they are exactly the same code, they're going to do exactly the same thing each and every single time. And that means that with the same defect in each redundant piece of software, I am going to have the same unsorted sequence of numbers come out the other end. Redundancy doesn't matter in software if they have the same fault. And this is the ultimate common cause failure. It's a very, very good example of how common cause failure can really ruin our day. Now, in hardware systems, there's an element of probabilistic nature. Sure, you might have the same incompetent installation team installing the shaft, those two pumps, but that's going to manifest itself in an accelerated failure in slightly different ways, but it will accelerate failure. But when you have the same defect in software, you will get the same failure at precisely the time that fault is uncovered. And so we can overcome this by using a different code for our redundant program. And so let's use a different code based on a different algorithm, which in this case is going to be based on this other algorithm called shell sort. And so now we do have 2 different components, so to speak, which are each supposed to be able to do the same thing. Because that one was written on a different algorithmic approach, it's highly unlikely that you'll have a fault that produces the same incorrect output in both components. But now the problem is that the software doesn't know which one of these 2 programs is right if they disagree. So if the bubble sort algorithm gives a sequence of numbers that differs from the sequence of numbers that is output by the shell sort algorithm, which one should the software use? Software doesn't know. So what we need to do for software is we usually have, when we want to do redundancy, we have 3 components, 2 redundant programs. And now we have a third algorithm, or third set of code based on the block sort algorithm, which allows us to code in a voting machine right at the very end. And essentially, this majority voter, will work out if one of these programs produces an output which is different to the other 2, then that output is disregarded. It's incredibly unlikely that different algorithms will have the same error caused by completely different defects. And also, if all 3 components, or if all 3 programs give you the same, give you different outcomes, then your voter is able to do this thing we call error handling. It says, look, all these, you 3 programs are telling me 3 different things. All I know is that I don't know. And that means you can program your software to raise a warning or raise a flag that your numbers are not sorted. And that can be very, very important because that allows human intervention. It allows you to abort that rocket launch because you know something is wrong. And knowing something is wrong is so much better than not knowing something is wrong. So our majority voter doesn't just work out if two of the outputs are the same. It also helps you work out some, identify scenarios where there is a systemic error where all three programs are giving you erroneous outputs. This is what we call N-version programming. And that N refers to the total number of programs you use to provide an output. And as a rule, it's minimum 3, and you'd ideally want to have different programmers using different approaches so that you the chances of you having overlapping defects or overlapping code defects is a very, very small. And when I say overlapping, it means that one defect in one program is highly unlikely to create the same set of erroneous outputs that another program would do, because would provide, I should say, because they are fundamentally and structurally different. And last but not least, we have human error, redundancy, which involves human error. And I've talked about this unfortunate incident a couple of times in previous webinars. Air France 447 crashed in 2009 over the Atlantic. Everyone on board died. And essentially what happened were the two pilots, the first officer and the co-pilot, in this cockpit were flying at perfectly fine. The aircraft was performing perfectly normally. Just after they crossed the equator, one of the pitot tubes froze up, which meant that there was an airspeed anomaly and the autopilot disconnected. Autopilot automatically disconnects when it is getting confusing inputs. And so the autopilot essentially disconnected and said, we have an airspeed anomaly. And essentially there were confusing readouts or confusing readings on the instrumentation, where it said the plane was traveling a lot slower than the pilots thought it should be. And when the plane is traveling a lot slower, what you should ordinarily do is dip the nose, push the nose of the plane down in order to gain speed, to then make sure you have enough lift over each wing. What you should never do is pull the nose up and try and climb. Now, for some reason, the first officer did just that on the right-hand side. Now you can see that you have two joysticks on the right-hand side of the person sitting on the right, on the left-hand side, the person sitting on the left. So one of the pilots on the right pulled back on the joystick because he was concerned that they were losing altitude. The other one was pushing forward, pushing down the joystick, because he knew that if the airspeed was low, you need to dip the nose in order to gain airspeed. The whole time, though, there was nothing wrong with the plane. It was traveling perfectly fine, and if they did nothing, everything would have been okay. Problem with that, though, is that this cockpit wasn't designed in a way to allow this mismatch of human inputs to essentially be recoverable. And unfortunately, the pilot, the pilot of the plane, who was asleep at the time, when he got to the cockpit, because the first officer and the co-pilot didn't know what was going on, he realized that one of the pilots was pulling back while the other pilot was pushing forward, without the other one knowing anything about what the other was doing. So they were sitting there happily, pushing and pulling joysticks in different ways, without knowing what the other one was doing, because it was dark and the joysticks were on the other side of the body, from the perspective of the other person trying to fly the plane. Now compare that to this cockpit. Now, obviously cockpits are very, very busy, but look at what we have that's sitting between the legs of each pilot. We have control yokes. They are visible, connected, and provide tactile feedback. Essentially, if one pilot pushes his or her yoke forward, it pushes the other yoke forward. And if there is a discrepancy, it's going to come down to whoever is the stronger of the two pilots, in a way. But what it does is straight away, it lets one pilot know what the other pilot is doing, because they can feel it. And this was not thought of in the joystick design for the Airbus aircraft that was unfortunately part of Air France 447. And so we often forget, or we often overlook, redundancy when it comes to human error or human interaction. This system here is by far the simplest and most effective way of minimizing human error when it comes to pilots commanding the planes to do different things. It is almost certain that if this cockpit or the control yokes were in the cockpit of Air France 447, that the scenario would have played out very, very differently. Within a matter of seconds, when the when the autopilot disengaged, one of the pilots would have known that the other one was doing something that they weren't doing. And a discussion would have ensued. And with any luck, they would have resolved the scenario very quickly and continued flying happily and landing safely in Paris. And so this just goes to show that you can design systems which are incredibly safe, and aircraft are incredibly safe. But if you forget about the humans and you want to have redundancy in humans, because you can see there are 2 seats here for a reason, then smart design and really thinking about human-machine interfaces really help you work out, can really help you overcome the losing redundancy where you think you have it. And so let's go back to what started this conversation. Fault tolerance is the ability of a system to not fail with the existence of faults. There are many ways you can deal with fault tolerance. You usually deal with fault tolerance when you cannot design individual components to be any more reliable than they currently are, and that includes humans. We can't design humans to be any more reliable than beyond a certain point. We can train them to a point. We can make sure that they have the necessary physical skills and unlikely to have heart attacks and everything else. But there comes a point where we say, you know what? When we have long international flights, we should have more than one pilot. But when it comes to working out how to solve fault tolerance through things like redundancy, remember, there is no such thing as redundancy, so to speak. There's no such thing as a laminated redundancy model. There's no such thing as a single redundancy configuration. Even when you have systems which look like they have exactly the same redundant configuration, the way the system uses those components can fundamentally change how the reliability characteristics of that system are influenced through that redundancy. You can see that William noted that the Qantas Airbus flight control problem with improperly flagged altitude data flagged as an angle of attack. Same thing showed up on three times on different aircraft. Labeling was done downstream from redundant computation, which is an example of where the redundancy is essentially overridden because of the design. And that Qantas Airbus flight, it came down to another form of redundancy where you had a highly skilled and highly qualified pilot stepping in and saving the day. Are there any questions on today's conversations? Any comments? Any bits of feedback on today's discussion about redundancy not being redundancy? When calculating system reliability, how is confidence level evaluated? For example, if we have reliability essentially for pump, reliability at pump 1, reliability at pump 2, what is confidence level of reliability, system reliability being 91%? What if the confidence levels are different for pumps 1 and 2? Well, that is a mathematical question. It's actually a statistical question, because if you can give me, for example, a curve which characterizes the confidence you have in your estimate of single pump reliability at 2 years, then I can give you a curve which represents the confidence you would then have in your 2 redundant pump system or 2 pump redundant system reliability at 2 years. The confidence levels are different for pump 1 and pump 2, that's fine. I can give you that answer. It all comes down to how you calculate that. Most of the ways we have confidence propagate through system reliability modeling is through many times assumptions and standard deviations this, and if this adds up to that, and the standard deviation of the system is a function of the standard deviation of the pump. But in practice, you can do it in a very accurate way using things like Markov chain Monte Carlo simulation to generate, let's just say, the perfect confidence curves of the system reliability based on those estimates for your pump reliability. That's where it comes down to how you calculate it versus how you model it. William said, depends on the confidence in the failure rate estimates. Little data, low confidence, lots of data, confidence is high. I would suggest, I would agree with that, but if you're able to capture it, whatever that confidence is, if you have low confidence, then you'll essentially have a curve which is very low on fat on your best guess for reliability. If you have a lot of confidence, that curve is going to be very high and peaked around your best guess. Either way, the approach is still the same. I sense I've answered your question, Kevin. So it was a good question, though. Any more questions or comments regarding when redundancy is not redundancy? Obviously, today's webinar didn't give you all the answers. We didn't tell you how to calculate, for example, the reliability of a switching pump, so a switching system with a reliability function for the standby pump in a standby state, another reliability function for the pump in an at-use state, conditional on the time the switch was triggered, combined with the reliability of the primary pump in operational conditions, combined with the reliability of that switching system. It is a challenging thing to model. Any recommended sources for further reading on standby switching CCF? I'll maybe talk about this offline. I do cover some of this stuff in my courses. There's not a lot of good stuff out there. You usually have two extremes. You usually have one extreme in textbooks where you have a very basic equation for dependent failure. You might hear about the perfect standby system. The reason why there's a perfect standby system is because that makes a relatively simple equation, not super simple, but it allows you to write a simple equation in textbooks for a system where you switch from a pump and the switching system is assumed to be perfect and the redundant pump is assumed to also be perfect when it gets switched to. And you see that equation in textbooks because it's simple. And the real equation is a little bit more complicated. Then you have university professors, those ponderous professors who have alpha factor, beta factor, gamma factor, all these sorts of weird and wonderful different models which incorporate common cause failure characteristics. But realistically, they're so complicated and so complex and rely, to be honest, on a bunch of assumptions for that model, I should say, to be valid, that it becomes beyond the remit for practical use in a day-to-day operation. So you might have to reach out to me after this. John. William, you said complex software failure rate estimation. Just to be clear, failure rates are not what we talk about here. We do want to talk about reliability, and I understand you can calculate reliability from a failure rate curve if you have it. If you're going to characterize the reliability of a system with a failure rate, nothing else, essentially assume it has a constant hazard rate, then the inaccuracies with your reliability model is already so shot that there's no point trying to be any more sophisticated than having by introducing common cause failure. So just to be clear, we need to focus on reliability curves and our confidence on those reliability curve points at certain times. Any more questions? Any comments? Well, thank you, Michael. You're welcome. No worries. Thank you, Kevin, for the feedback. Well, Fred, we're 2 minutes under the 60 minutes, and that is got to be a record. Thank you, William. I usually finish about 5 minutes early, and then we keep talking for the next few days afterwards before you stop recording. But I think we're good for today.
Well, you can chalk it up to that random hand of chance or
Right.
random...
Yep. Yep. Didn't include that one today.
I thought that was required. It's sort of like having a bathtub curve in a reliability book.
Well, it was a requirement that obviously failed by traditional definitions of failure.
Yeah,
but,
we'll try again next year.
Yeah, we'll see how we go. Yep. Or I could just assume it away. That also works, doesn't it?
Yeah, no worries there. All right. Well, thanks, Chris. We'll look forward to next year's round. Have a great set of holidays. And thanks everybody for attending. And we'll see you all in the next round of webinars.